Let me just go through what I'll be covering in this presentation. I hope I'm audible and clear enough.
Yes, Mr. Anmol, go ahead.
Okay, thank you. So what I'll be discussing is what is the theoretical understanding you get in your academic syllabus versus the practical application. Who are the major employers, right? I'll take you through a couple of very simple sample lessons to understand the behavior of structural engineering through deflection diagram. It will be less of mathematics, more of imagination. Okay. I'll discuss in detail how to solve the increasing strength of beam or passing a beam under a load. I'll just make you go through other of couple of basic checks, which are subsidiary ones, and I'll discuss very simple basic case scenarios, which are building blocks of any structural frame. Okay. So what you go through in exam syllabus is really very different from what is required in industry requirements. In exam, you get a simple portal frame, you get the loads on it, you derive forces. Whereas in structural engineering, you will need to create the geometry first. Okay, you need to understand the loading pattern, need to create the geometry which is more efficient in transferring of the load. It is more of understanding of physics because all the calculations will be done by softwares like StatPro. For superstructure, for foundation, we have Math 3D, and we have various other softwares. So what I want you to understand is to understand the approach of imagination and the physics. Okay, in academics, you would have learned methods like slope deflection method, moment distribution method, Carney method. I'll tell you straight away, none of these methods are used in practical application. What you need to understand is the basic concept of how every element behaves, how every element responds to the loading, and how the load transfer happens. Okay, so this I'll be covering through. I'll at least try to clarify the basic approach. Of course, I'll not be able to go in detail in these 45 minutes. For employment opportunities, I'll just share the relevant industries first. I'm from oil and gas onshore. There's an offshore division as well, which is a very niche division for structural engineering. Out of all the sectors, offshore oil and gas structure gives you the opportunity to be the dictator as a structural engineer in deciding the whole engineering plant. In onshore, piping and mechanical govern, they decide what will come where, whereas in offshore, it is a very specialized structural engineering branch. Structural engineers decide where will come what. And there are around 10 to 15 different kind of analysis, which are dynamic analysis. Going forward, we have power sector, that is the coal and energy sector. We have pre-engineered buildings. Pre-engineered buildings are basically your warehouses and industry sheds, which could be used for storage or even oil and gas onshore or power sector can use those. Okay. We have, of course, residential and office infrastructure, and we have miscellaneous infrastructure like stadiums, malls, etc., high towers, and we have telecom towers also. I'll just list down few major employers: L&T Hydrocarbon, from where I belong, Power, L&T Power, L&T ECC, L&T Heavy Engineering. We have the Reliance Group of Industries, Shapoorji Pallonji, and Afcons, which itself is a big conglomerate, is just a part of Shapoorji Pallonji. We have many opportunities in Afcons as well. Lodha Infrastructure, GMR. We have Adani Group. Adani Group has majorly power sector, and he is also coming into renewable green energy plants. Okay. Rest of the companies like Flo Daniels, Bechtel, Samsung, Aker, Siemens, Toyo, GS, Kane India are all oil and gas sector. Similarly, Shell, GE, Punch Lloyd, Tata Projects. Tata Projects is, I think, into power sector also. EIL. So EIL, PDIL, GACL, HPCL, ONGC, GSPC, these are all PSUs. You can crack through MTech. We have other companies also, Modic, Black & Veatch, Trine Energy, from where I started my career. Amec Foster Wheeler is a UK company, Simplex and Gammon. So I've majorly listed oil and gas companies because that is sector I came from. Uh, you can have actually better opportunities outside as well if you have time and money to invest in a MS, go to US or Australia, study there, and get a degree on that basis. If you get a job there itself, it will be of much higher value than what you get in India. So let's start with the sample lesson. This is a very simple portal frame, fixed connections, fixed joint, and a loading in middle. Please just take 2 minutes to draw a deflection diagram and a moment diagram if possible. Then we'll discuss. You have to just understand how the loading will happen, how the beams and column will bend. That's it. Even if you draw just a reflection diagram, it is enough. So this is a very basic element of the structural engineering, which I have observed that even people who are passing the engineering and coming into office, joining the profession, they are not able to understand this. They have solved all of these things in engineering, but when they come to practical application, the simple elements fail. That is a purpose. Okay, so I'll move forward. So this is a basic reflection diagram which we get and the moment diagram. But the idea is how to approach it, right? I'll start with my own diagrams. This is the portal frame. We have the loading here. If I draw the reflection diagram, simple, it will bend like this, right? There's a loading in middle. If it would have been a thread, just a thread, and not a stiff beam, then thread would have hanged like this, right? And this is what we get in moment diagram. So yeah, so this is reflection diagram of the beam. What is happening at column beam junction? So this is the 90-degree angle which is before loading, and the connection will try to retain it as such. When it is bending, the column will try to deflect outwards. Okay. Why so? Because this 90-degree angle is being distorted by force or by this force. So column will try to deflect outwards and beam will also try to deflect outwards just to try and retain this 90-degree. Okay. Similarly, when we go to the fixed joint, this column is already trying to rotate outwards to retain this 90-degree, but we have fixed connection here as well. Here also, but now we have to retain the 90-degree angle, and this will create a negative moment at the column support junction. And symmetrically here. Okay, so we'll try to draw the moment diagram. Of course, we have this part. Okay, since it will try to rotate like this to retain the 90-degree, we have some negative moment at the end. We have similar negative moment will transfer to column and the support. Very simple approach to draw the moment diagram, right? Okay, so moving on to next example. If you have any queries, we'll solve it after the end of presentation. I make a slight change. I shift the load towards left of CG. Okay, the CG would be of this frame is somewhere here. Earlier the load was here. Now I have shifted here. Now just draw a deflection diagram. Even if you don't wish to draw the reflection diagram, it's okay. Just let me know how this frame will sway. Will it sway at all? Because it's just a vertical loading. If it will sway, where it will sway? Will it sway towards left, right, or it will not sway at all? So these are the three options. Jen, is it possible to have some responses from the participants on this? on Zoom chat. Participants can directly uh, write to in the chat. I just need a quick kind of poll, left, right, or no sway. And if possible, just let me know how many are left, roughly more or left, more or right, or more of no sway. What are the answers from the participants? Because I'll not be able to see the chat when I'm sharing the screen.
So Anmol, Mr. Praful says it's right.
Okay.
And a few more are saying it's left.
Okay. What are the more number of answers, left or right?
Okay, Mr. Shubham says it's no sway.
No sway, okay. Which are more number of answers, left, right, or no sway?
Okay, exactly right.
Approximately, it's coming to right?
Yeah.
Okay, good. So it will sway towards right. For those who have not got the answer, I'll just
What
walk
is
you
the
through.
answer then?
So answer is right. Okay.
Okay.
It will sway towards right. Now let me just tell you the approach. And even people are not able to understand how to approach it. So we have shifted the load towards left. Now, sometimes it seems that it is to the left of CG, and that is why the frame should sway left, but it's not the thing which actually happens. I'll tell you how. So when we have load shifted towards left, the first column which is getting this load is the left column, right? This column will take more of this load rather than this. This angle will be distorted more, this will be resisted more. If I draw a free body diagram, okay, I separate left half and right half. This will make the left column bend towards right because it will act as a cantilever. For the right column, the loading will be less. It will, ideally, if it's just this column present, this part will bend towards left, right? But since loading is more closer to this column will be the first to react. This deflection will be higher than this deflection. And hence the whole complete frame will bend towards right to minimize the internal forces. So I'm happy that people joining this webinar have this concept understood. Okay, so I'll now discuss the case of increasing strength of beam. Okay, so this is a beam, we have cross-section I-beam, most commonly used in steel structures. Have cut the axis around about major axis. The case is if the beam is bending about major axis, how to pass it simply. Okay, this is a structure, how to pass it. One of the option we have is increase the beam size. Simple. Okay. Now we have this beam. Okay. There are two ways to increase the beam size. Either increase the weight, that will increase the thickness of flange and web, or increase the height and not increase or maybe decrease the thickness of flanges and webs so that they are of equal weight. Okay, but how this will help? It will increase the moment of inertia, right? Very simple. We have the AY square component for moment of inertia, and more it goes towards away from the center, the higher moment of inertia. This is one way, but what if we have a pipe going in below it and we cannot increase the beam size? The top level is usually fixed, so we cannot increase from that point as well. Second option we can look towards is add plates. Okay. Now where to add the plates? This is the beam. Okay. There are three options. I can add a plate here. I can add a plate here. I can add a plate here. Let me just mark these options A, B, and C. Okay. So when I'm adding a plate A, it will increase the shear resistance because it is acting along the web in the vertical direction. So whatever the forces are, if it is crippling under shear, then it will increase the strength of this beam at that particular junction. So if a load is here, we might just add plate on the web in this segment only, need not add throughout the length, right? Or maybe at the near the supports where the reaction will come. If I add plate here, it is not much of use for bending about major axis. If I add a plate here, that is what will help me. That will increase the amount of inertia similar to what we had in here in this example. Okay, this will increase one more element, VD cube by 12 plus AY square. Okay, so if I add a plate here, it will not add to the moment resistance about the major axis. It will add a moment about minor axis. So let me take a different color. This is the minor axis. So if I draw the top view of this, if a load is acting this way, there are horizontal forces, okay? It will deflect like this, right? This is where this plate will help, the plate B. For major axis, we have to go with plate C. For shear forces, we go with plate A, right? But sometimes, again, the location constraint may be there. We might not be able to add the plate. So what is the other option? We can decrease unsupported length. We can add a bracing. This is called knee brace. The moment is for a uniform distributed load, it is WL squared by 8, right? If I decrease this, then I'm decreasing by 2 degrees the whole force. Okay. So if I add a knee brace, then it will decrease the moment and beam will be passing. Is the moment connection possible? So right now, of course, we have discussed already the moment connections only, but what if we have a pin connection? The rotation is allowed, right? Now, if there's a load here, the moment will be like this. But if I make a moment connection, okay, the universal symbol for column beam moment connection is this. In the drawings, I'll just try to make it separately here. So this is a universal symbol for moment connection. Okay. So if I create a moment connection, then this whole curve will shift towards top, right? And it will also transfer the forces to column. The column is participating in this transfer of forces, internal forces. Okay, and it will decrease the moment on the beam, and which we can pass it later. We can add a horizontal bracing. Okay, so if you see this small 1x1 beige unit, let's say this is where the loading was happening. Okay, big loading, and this beam is failing. I added a horizontal bracing. Now, how will this help in vertical load transfer? This is a horizontal. There's not in the same plane, which is the load of, the vertical load. It is in horizontal direction. Any answers? Please, host, please let me know the answers, 2 or 3 from the participants. Why is this happening? Like how this horizontal bracing will help me better transfer the load, not better transfer, but increase the strength of the beam for vertical loading.
It increases the stiffness of beams.
Stiffness of beams? Okay. How come? This is not increasing the stiffness of the beam. No, in a way, but how? It's not directly. What
I
is the
think it
concept
makes
called?
more intermediate structure.
Please come again.
I think it makes more intermediate structure.
Intermediate structure? I didn't get the meaning.
Yeah, so there
So,
are varied answers.
okay, no worries, no worries. So, I'll just share the answer. The exact answer is lateral flexural buckling. It restrains that. Now, in your design, IS 800, you would have learned two kinds of beam design, that is laterally restrained and laterally unrestrained, right? This beam is not being laterally restrained from any point until unless I add this spacing. Now, how this actually happens? What is the concept of that laterally restrained beam? Okay, so when a beam is bending, okay, the moment is like this: the top flange, there's the bottom flange. Okay, this is the moment. This will be in compression. This will be in tension. So in compression, any element, whether it be column, a part of column, a beam, or whatever it is, it will fail first through buckling. Okay, what is buckling? I hope you remember. If there's a force here, it will not crack it immediately. It will first buckle. And that is where the failure mode starts. Okay, so only the compression flange comes into buckling. And what happens is it tries to bend torsionally also. This is a beam. Because of buckling, it tries to move torsionally also. That is why it is called lateral torsional buckling. And when we add this bracing, we are restraining this top flange. Okay. Now in industry, there's a very important point. Sometimes people add bracing here. Okay, this is the gusset plate, and they will add bracing here because there are many other beams going on. It is difficult to pass. Not difficult, but sometimes they prefer from column to column bracing, end-to-end bracing, and that is why they surpass all the beams, all the intermediate beams through bottom, and they connect it to the tension flange. This will not help in restraining the compression flange. This is very important to note. Okay, so you have to try to make the connections through top flange only. Then only the beam is the slenderness ratio about the minor axis will decrease for compression flange. Okay, there's one more way, one more innovative way, which is not written in codes, which is really sometimes understood. What you can do if you don't have space and you are adding a bracing at the bottom of tension flange, just add a stiffener, right? It will help. It will help for compression flange and tension flange to work together, to behave together, to respond together. So if there's lateral torsional buckling, it will pass this force to this, and it will have a reaction from the bracing. Very crucial point, which many engineers miss, even senior engineers. Okay. Suppose there's a plate here. Okay. And this beam is thoroughly connected to that plate. It makes it a completely restrained, literally restrained beam. And you can take the slenderness ratio near to 0. That will increase the beam strength to a very high capacity. This is only when there's a plating there, but mostly it is grating, okay, which is used for walking. So I'll just walk you through the other basic checks, serviceability checks, which are usually there. That is a deflection check. This two clauses are from the IS 800 code, but it is more dependent on the design specification of the project or the client. Okay, usually we allow height by 200 deflection, okay, in industry, and L by 325 as vertical deflection. This is from column to top of the column, or even this part of the column. Suppose this is okay. For this portion, you will take this much as L, edge. For this portion, you get smoothest edge. The deflection, what you get due to wind load or earthquake load, it should be within this limit. And this is for the beam, L by 325. Either 300 also sometimes, depends on the project. For gantry girder, it is more stringent. Mostly uses L by 750. We need to minimize the reflection. And gantry girder design is a bit more specific, which we can take a bit later. And the slenderness check is also one of the design parameters in STAAD. Okay, most commonly used is 180 and 250 and 400. 400 is by default for tension members. Okay, for any compression member, because buckling is the governing force, we take 180 allowable KL/R. For beams, if there are horizontal loads apart from wind and earthquake load, then we have to take 180. If there is only horizontal, if the horizontal forces include only the wind load and the earthquake load, then you can take 250. Okay. So I hope you understand the slenderness ratio when you are finding the unsupported length. You are giving a K factor or unsupported length factor in STAAD as a specification and design parameter. You have to understand the end connections. Okay. Suppose it's a, let me remove this joint. Let me make it a beam. Okay. Suppose it's a fixed connection. This is a fixed support. This could be 0.8. Okay. If it is a pin, if it's a cantilever, okay, then the deflection will come something like this. Okay, so the unsupported length becomes twice the L. Okay, so sorry, just a second. So if there's a this complete restraint, only then it is 0.8. And if it's a column beam moment connection, then it varies from 1.2 to 1.5. Now this 1.2 to 1.5 varies on the stiffness, relative stiffness of column and beam. Okay, if column is more stiff, much higher stiffness, then the KL/R, the K factor we take 1.5. If it is near about the beam stiffness, then we can take 1.2. This is also very crucial because there are sometimes frame very small. This length is very small as compared to this beam length, column length, and the stiffness will be very much high. In this case, you take 1.5. Only when the end part is completely restrained as a support, then you take 0.8 or 0.7. Very basic concepts you need to know. Okay, I'll just take through a couple of case scenarios which are building blocks of a frame. I'll just tell you how we just play around with bracings and the column orientation when we are passing a structure. So if there's a load here, this is a portal frame. Okay, this is a portal frame, and these two frames are jointed by bracing. Now the orientation of the columns here is like this, right? They don't have really the moment capacity in the minor direction. That is where the bracings come. Okay, here the moment will be only in this direction, and the shear force will be, of course, in both direction. Additional force could be tension and compression due to this force, this bracing. But of course, you need loading in this direction also. What could be the other way? We could just add a small bracing here, which helps me transfer this load. It will still be a frame with column orientation like this, but you can make this pin connection instead of moment connection. Here we have moment connection as a portal frame. Here it will decrease the forces on the column. It will reduce the column size. What will be the addition? That is the bracing weight. Okay, so you are reducing the column size by adding the vertical bracing. This could be more optimized than this. Who knows? You have to see which works best for your structure. This is where hit and trial comes. Another case scenario. I change the column orientation to like this, from like this, okay? Add the bracing here. And now the horizontal forces are getting transferred through bracing. There's no horizontal force here in this direction. So column size is less, even though this is a bigger portal frame if we consider from the size perspective. Okay, what other things you could do? You could make it a pin connection between column and beam. It will further decrease the size. Okay, but if there's a loading coming here, then you need to see which is more optimized again, either the bracing part or the column orientation around along this axis. So now there's one more building block of the structure. That is the anchor bolt arrangement. Now, anchor bolt arrangement is so much complex. Not anchor bolt arrangement, anchor bolt design. That the whole chapter, whole appendix is there in appendix ACI 318, appendix D. There are 4 kind of cases, each for tension and shear for anchor bolt arrangement, because there is a concrete and steel interaction, which is pretty complex. The load transfer from steel column to concrete column is pretty complex. There are different kind of failures. There are breakout, there are pry out. Maybe concrete will fail more earlier than the anchor bolt made of steel itself. This is pretty complex, but I'll not go through that concept now. What you need to know for interviewers for entry, gaining the entry in this, is what I'll discuss. Okay, so there are various kind of bolt arrangements you can see. Some of this will be pin connections, some of this are moment connection. Some of this, the moment connections which are around about one axis, that is a partial moment connection, or a fully moment connection. So if this forces, we don't have, for this arrangement, we don't have any bracing, then this could be a moment connection in both axes, because these 2 anchor bolts will participate in transferring the moment. But if this bracing is here, then this will become a simple pin connection in this direction, and these bolts will take the moment only about this direction and not about this direction. Okay. What could be the forces? Of course, we have shear force. For any column, we have shear force in X or Z. The resolution A square plus B square, root of that, will be transferring through to all these 4 bolts, okay, equally, because they have equal capacity. We have sometimes pure tension. Okay, this is a frame. We might have as a fixed joint. If any force is coming here, this support will only have tension forces. Okay, and this will be transferred to all the bolts equally. Again, very simple. But there are moment forces also in a portal frame. To resolve the moment forces, what is the simple criteria? Simple. We have to take the lever arm from bolt to bolt and apply the force, apply this formula M by D, M by lever arm, moment to divide the lever arm's force. And when you have many bolts, you take the polar moment of inertia to resolve it. Okay, so in here, one bolt will be in tension, the other may or may not be in tension. Okay, I'll just, this is the bolt. Okay, now the moment diagram might be this force distribution could be like this, but this part comes in compression and the bolt will not participate. It will be taken by the concrete pedestal here, but it could also be that the forces are so high that this bolt also comes in tension and this bolt also comes in tension. This bolt will be critical because it will be carrying higher forces. So this is also resolved in tension, and we have formula shear force by shear capacity should be less than 1. This is after factor of safety on both load and design. Okay, tension and tension capacity should be less than 1. When we are combining these forces and checking the combined capacity, this is the formula. We take the square and should be less than 1. According to design specification, the formula could also be less than 1.4. So what you really need to understand is how you divide the forces of moment into volts. Okay, polar moment of inertia you take, and the basic checks of anchor volt. That is all I'll discuss in this presentation of mine. And with this, I end my presentations.